In the United States, with a crane that was never built for glory or headlines, but for a problem so big it threatened to shut down an entire industry. Nuclear power in America had reached a standstill. Costs were skyrocketing, projects were stalling, and part of the problem was simple. The equipment needed to assemble reactors didn't exist. That's when American engineers decided to create something new, something that could finally give nuclear construction a fighting chance. The result was the Bigge AFRD, the A-Frame Ring Derrick, a machine with enough power to lift over 4,000 metric tons, more than 4,400 US tons, straight into the air. To put that in perspective, imagine stacking 30 blue whales together and holding them steady hundreds of feet above the ground. Its boom could stretch 560 feet high, towering over its job site like a steel guardian.
Lifting of concrete blocks to ensure that the capacity of the crane can lift as designed and can do so safely. In this case, the crane was tested at 100 to 110% of its largest lift, which is 1,520 tons. The HLD's first lift will be to take the nuclear reactor vessel off the rail car.
But this crane wasn't about moving fast or traveling far. It was built for one thing: stability. Anchored to a giant circular concrete foundation, it could swing 360 degrees around its site, but never leave it. That was the trade-off: brute strength without mobility. And yet, that was exactly what America needed. At the Vogtle Electric Generating Plant in Georgia, the AFRD was tasked with lifting massive nuclear modules, steel containment rings, steam generators, and components weighing millions of pounds that had to be lowered with millimeter-perfect accuracy. Picture this: workers standing far below, guiding the placement of a 2 million pound structure, knowing that a single misstep could endanger the entire project. Every lift felt like holding your breath. The tension was electric, but the crane delivered over and over again, proving that large-scale nuclear projects were still possible. It didn't just lift steel, it lifted the hopes of an entire industry. Still, as groundbreaking as the AFRD was, it carried a limitation that no one could ignore. It was tied to one site. What if a project needed that same raw power but spread across a massive footprint with dozens of lifts in different locations? That's when the world turned to Belgium, where engineers dreamed of a machine that could combine strength with mobility. And out of that dream came Big Carl, the CRANES SGC-250, a crane so extraordinary that some people call it the most impressive piece of mobile machinery on Earth. Where the AFRD was a titan rooted in place, Big Carl was a titan on rails. With a lifting capacity of 5,000 metric tons, over 5,500 US tons, it had more muscle than its American predecessor. But more importantly, it could move with its load. That single breakthrough changed everything. Big Carl could pick up a prefabricated module weighing thousands of tons, swing it smoothly across a job site in a full circle, and place it exactly where it was needed, all without being taken apart and reconfigured. Months of construction time saved, millions of dollars were cut from the budget, and all of it was possible because of a slewing ring and rail system that kept the crane perfectly balanced, no matter which way it turned. The UK's Hinkley Point C nuclear power station became Big Carl's stage. When the crane arrived, it came in 280 separate truckloads, assembled piece by piece over months until it towered 820 feet high. Once standing, it became the beating heart of the project. Every colossal reactor dome, every prefabricated steel ring, every massive component, Big Carl lifted them all, and it did so with a kind of elegance that was hard to believe for a machine of its size. Its hook block alone weighed over 100 tons, heavier than a locomotive, while 12 engines worked in perfect unison to power the hydraulic systems. Watching it in action was like watching an orchestra, every movement controlled, every detail precise. It wasn't just a crane, it was proof that size didn't have to mean compromise. Power and mobility could coexist, but human ambition never stops at good enough. As Big Carl dominated headlines and transformed projects, a new question emerged. What if we could go even bigger? What if we could build a crane so powerful that it could handle loads previously thought impossible, lifting entire structures that no engineer dared design before? That vision gave birth to the Mammoet SK6000, the crown jewel of land-based lifting. The SEK6000 isn't just the next step up, it's a leap into another dimension. With a certified lifting capacity of 6,000 metric tons, nearly 6,700 US tons, it can raise over 13 million pounds in a single lift. At that scale, numbers lose their meaning. Imagine an entire apartment block, or the weight of hundreds of fully loaded semi-trucks, all hanging from a single machine.
Testing plan, especially for the SK6000, so we can test all the separate parts of the crane. First test here was with a 1,500 tons tray. That was first the static load, just lifting it up.
Designing the SK6000 wasn't just about scaling up. Every detail, from the hook blocks to the cables to the foundations, had to be reimagined at the cutting edge of material science. The stresses at those loads don't just test steel, they test the limits of physics. And yet, the SK6000 wasn't built just to be the biggest trophy crane in the world. It was built for the future. Offshore wind turbines are growing into giants themselves, with blades longer than football fields and foundations that weigh more than bridges. Industrial facilities are turning toward massive prefabricated modules, built in factories and shipped whole to their destinations. The SK6000 is designed to lift these next-generation components in one go, making what would otherwise be impossible, practical. Of course, building a crane like this is a gamble. Development costs ran into the tens of millions, and Mammoet had to bet on industries that don't fully exist yet. But if the future does demand cranes of this scale, the SK6000 will be there waiting, standing as a machine built not for today's challenges, but for tomorrow's ambitions. It's more than just engineering, it's foresight cast in steel. And when you step back and take in the sight of these three machines together, you begin to see more than just cranes, you see milestones in human ambition. The American A-Frd was a lifeline for an industry on the edge of collapse, proving nuclear power could still rise when many thought it was finished. Big Carl followed, not only stronger, but graceful in motion, a giant that could glide across a job site while carrying thousands of tons, rewriting the rules of mobility. Then came the SK6000, Mammoet's audacious bet on the future, built to handle tomorrow's problems before they even arrive. Offshore wind turbines taller than skyscrapers, refinery modules the size of city blocks, structures so immense they once lived only in theory. Together, these machines form chapters in a single story, proof that when humanity faces challenges that seem too heavy, too complex, too impossible, we refuse to back down. We build, we innovate, and we always find a way to lift them. So here's the question, have we finally reached the ceiling of what's possible? Or will we one day see a 10,000-ton crane rise, dwarfing even the SK6000, lifting not just steel, but the limits of our imagination? Whatever the answer, one thing is certain. Machines like these are proof that dreaming big isn't enough. You have to build big too. If you enjoyed this journey into the world of giants, hit like, subscribe, and turn on notifications, because the next machine we cover might just blow your mind. Until then, keep your head down, your gear running, and remember, there's no such thing as impossible when you've got the right crane.